can look at so how the luminosity is defined and the formula for the assuming the Gaussian profile of the bunches, right? And there is like 4 pi and 2 sigmas coming up. So you're from the theory and you're flexible with integrals. Can you just get me this formula and prove that it's correct? Just for you to probably it will take more than 1 day, I don't know. So let's try.
1 day. It should be like 2 minutes.
2 minutes, okay.
Yes.
And we can discuss it in the evening. So that. And the second, so remember we discussed like how many events we can get and what is the cross section. Yeah. So for the AC. So I have 4 cases for you, and maybe you can calculate the number of events. The neutral current, 2 square greater than 0 mean bias events. Roughly, so we have 100, but if you look at the particular energy, it will be close to the 50 microbarns. And if you can calculate number of events per year and per second, assuming 100 inverse femtobarn luminosity per year. Boson-gluon fusion, CC bar production, cross section is about 60 nanobarns. The same question, like how many events. Charge current, where we have neutrino in the final state. So W plus minus direction, 100 picobar. And my favorite process beyond the standard model, leptoquark production. Anyone knows what is leptoquark? Raise your hand. So this is boson, the same as Z, gamma or W, which converts electrons to quarks and vice versa. Yeah, so it's boson. And in theory, beyond the standard model theory, you can produce leptoquark, you can measure the widths, and right now the Monte Carlo shows that the cross section is about 1 femtobarn. So, no, just the question: will we have a chance to see at least 1 leptoquark? Maybe in a year, in 10 years, or how many events we can get? Okay.
Is there a mass range for
the leptoquark?
Yeah.
Assume this cross section. It's everything in there, mass and coupling. And just if you will see the one, not one, so we need some fraction, 10 sigma or whatever, 3 sigma. Will we have the Nobel Prize or not for discovering? Okay, let's start with the detectors or continue with the detectors. So we yesterday we talked about solenoids, tracking, and the colorimeter partially. So today we are going to dive into so I will continue with hadronic colorimeter, and then we go to the particle identification and forward, backward instrumentation, and how we actually simulate and collect data. So just to remind you, this is our central detector, general purpose. We talk about the tracking system here. So and now we continue. Remember, I mentioned yesterday that I forgot to include one slide. So this is sort of show you the different concept of the silicon detector, hybrid pixel detectors, where you have the front-end electronics bonded to the silicon substrate, and then we have MAPS detectors with a rolling shutter. Just to remind you 2 different perspectives. And so this sort of concept we are going to use for the time of flight detector, so that for you to understand. So you see the lot of materials, but nevertheless, there are some benefits, and maps are slow, so they are collecting the readout time is about 2 to 6 microseconds. Actually, when you will do the calculation, you can even calculate how many events we can get per like, their integration time to the detector. Yeah. Integration time is roughly 2 microseconds. So we discussed yesterday about event kinematics. So we have a scattered electron, and as you look at the formula, we just by measuring the scattered electron, we can identify, with simple formulas Q square, Y, and X. But there is some limitation with that. Yeah. So first of all, the Q square, as you can see, has a linear dependence on the energy of the scattered electron. Unfortunately, this method has some, drawbacks. So we can only apply it to Y below 0.1. Yeah, so it's actually this band. Yeah. Yeah, this area. You can see the green dashed lines here. So this is Y equal 1, Y equal 0.1, and Y equal 0. So now let's talk how can we improve this. And another method is just to look what is going on with quarks or with hadrons. And so I show you this plot already. So as you can see, the kinematic EIC is boosted. That means the higher the energy of the quark, more high X and high Q square events we're going to touch. That means we have to really put the emphasis on the hadronic detection in the hadron and cup area. So there's 3 methods which actually require also detection of the hadrons. One we call the sigma method. It doesn't depend on the initial electron beam energy, which is really good because there is less influence by the initial state and various radiations. There is a double angle method where you only calculate X and Q square and Y using the angles of the scattered electron and this jet. And there is some drawbacks for all of those methods. And the one method which calls the Jacques-Blondel method requires, only relies on the measurements of the hadronic final state. And it's very poor compared to all other methods, but this is the only method for the charge current reactions where we have neutrino. And as I mentioned yesterday, so we are not detecting neutrino. That means the way how we identify charge current events. So we have the missing PT. Yeah. So we have jet in one direction and nothing pointing to another direction. And this is the method actually we can use. Of course, nowadays with machine learning, we can get information from all particles, feed it to the machine learning tools, and try to improve. For you, try, maybe you will succeed. We are right now looking at the various methods for them. So a few words about charge current. I cannot really skip this because this is really important for me. My favorite topic, again, beyond the standard model of physics. As you know, the charge current reaction has the linear dependence on the polarization. And we can use actually this effect to study the right-handed double. By measuring the cross-section with a different polarization, we can predict if it's 0 or not, cross-section going to 0 or not. And this is why we need a really good control and systematics on the lepton polarization. It's one of the aspects of the requirements for the EIC. And of course, it would be nice to have positron beams. Again, a few words about charge currents and the missing PT. So for the if you plot the PT of the hadrons, you will see this dependence. The higher PT, the more high X physics we are sort of passing. And the question is, so missing PT about 10 GeV corresponds to the Q square cut of 100. Yeah, so this is sort of the corner where we are going to explore the charge current reaction. Why I'm saying this? Because, first of all, I showed you this imaging detector, so we need to really understand the hadronic final states, not only the electromagnetic showers, but also hadronic. But some of the we need to understand how the shower is developing, because we would like to understand improve the measurements of the hadronic final state, and we would like to understand what is the substructure of the jets, right? That's why we are thinking about those imaging, and under the jets, if you ask actually Google, so this is what we will get, right? But in a experimentalist particle point of view, this is number of collimated tracts which leaves the energy in calorimeter. So this is what I see when some people were talking about jets. For the theorists, of course, this is particles, quarks and gluons, associated to the strong quark. And now the question is how we do the identification of those jets. And so I added here one slide. So we have multiple methods. One is just you draw the cone, and then based on look at what are the small particles which you can link to this cone, and you sort of sum them up. And the second method, which calls the KT, so you just look at the transverse momentum kick with respect to the sort of the prime particle. And those methods have also advantages and disadvantages. And of course, nowadays we are trying to apply machine learning, so to get better understanding if these particles really belongs to the jet or not, because the better we understand the jet, the better we know what is the corresponding struct work energy. So particle flow, why did such a strange? Okay. Look at my PDF, so I probably some conversions. So this is the algorithm which experimentalists are using in order to improve the measurements of the jets. We know that the jet consists of 60% of the jet consists of the charged hadrons, 30% of the photons, and 10% of the neutral hadrons. And as I mentioned yesterday, so we can get very, very good measurements of the particle track. And if we have the PID, so we can identify what will be the energy of those charged particles. That means we already very, very precisely measuring this 60% of the jet energy. Then we have the photons. Okay, we measure this electromagnetic calorimeter, and only the leftover is the 10% for the neutral particles. And this is, why we need the hadronic calorimeter. And in a typical approach, we just, the jet was the sum of the electromagnetic calorimeter and hadronic calorimeter energies. But nowadays, with this, the fancy granularity calorimeters, we can really improve the performance. And the one slide for you why the jet identification is really important. First of all, to look at the substructure of the jet. There is a tau jet, and we have to identify if it was a gluon jet or tau jet or heavy quark jet with displaced vertex. So this is really important when you do the reconstruction. So now let's go back to the hadronic calorimeters. So as I just said that for the hadronic calorimeters, we mainly detect neutral particles, neutral hadrons. But of course, there is an energy. We measure the energy of the charged particles, well, charged hadrons. We have again fully hermetic hadronic calorimetry at ESC, and let's just go one by one. So for the backward end cap, so this is the electromagnetic, there is electron end cap where the scattered electrons are going. We are planning to reuse some star colorimeters, omega tiles, and it will be only 2.4 interaction lengths in the size because we do not have a space there. But nevertheless, with such a design, we can achieve quite good energy resolution. So it's about 70% of a square root. So those steel blocks will be sort of alternating with scintillators. For the barrel, we are repurposing S-Phoenix barrel HCAL. You can see the new magnet will have the same sort of dimensions, so we can repurpose this. Of course, there will be some upgrades, so like CPMs and readout will be replaced, but the majority of the colorimeters will be repurposed. And of course, we need to make sure, because the hadronic colorimeter are the largest, we need to make sure that everything fits into the door and into the experimental fields. Else? Yeah, and right now, I talk about the interaction list, so the total size will be about 4 interaction lengths. For the forward end cap, so this will be concept based on similar to the Kelly's HCAL. And we are going to use the various layers. So there will be 4 layers of tungsten and 61 layers of steel. And in between there will be the scintillating materials. So all in total, we have this. There is the. I think it was. Oh my God, where is the number? Yeah, 7.5 interaction lengths all total. But again, so the space is quite tight. We cannot really squeeze a lot of materials what we need, but we have to live with available space. So those colorimeters will have 2 sections, so we will open them, close, so that we can get into the inner part of the tracking detectors and the other sub-detectors, which are closer to the IP. So they will consist of 2 parts, and we will roll them in and out, what needs to be done for the maintenance. And you can see how the bricks will be located around the beam pipe. Resolution is quite good, so it's 45% of a square root of E, not bad. I mentioned yesterday that the beam pipe, because it has to accommodate the crossing angle, will be really weird. So we cannot really cover all the area. That's why the concept came that let's cover this area which are very close to the beam pipe. As you can see, the colorimeter is asymmetric. Yeah, the beam pipe goes under some angle here. So let's cover this the part, because this is one of the most important part, because all the jets and the remnant will go into this direction. Let's cover this with high granularity, or insert, what we call the insert. It will have alternating layers of the steel, and then tungsten and steel. And with scintillators, you see it's like a honeycomb structure with CPMs attached to each of the cell. So this will provide very good resolution and angular resolution of the jets. And so on. Yeah, so what else? I think this is, oh, right, it's not.
Is it not clicking?
Yeah, no. It's come. So what is also important for the detectors is to see what is the dose which they will accumulate over the running period. And as you can see, there is some hotspot in the hadron end cap and close to the beam pipe. So this will be one of the hottest area of the detector. So I think that's all what I have for the colorimetry. Now let's talk about the particle identification and the mass. I showed you this table with our detectors, but I didn't mention how we actually identify the particles. So let's just go one by one. So as you can see here, we have the electrons. They provide, they leave the particle track. There is the energy in the electromagnetic colorimeter. And we can say, okay, this is the electron with certain probability, right? Photons or gammas are not leaving the track, but they are depositing energy in electromagnetic colorimeter. For the charged hadrons, some of them, depending on how they interact with the material, they can or they cannot leave any energy in electromagnetic colorimeter, but they will dump the full energy in the hadronic colorimeter. And this is actually the problem, how to say if that was the electron or if there is like hadrons. Yeah, so we have to understand what is the electron hadron separation of each of the detectors which we are using. But we cannot really identify the type of the hadrons. We cannot say if it was a pion or kaon or proton, so they will all behave identically in the detector. Neutrinos, we are not measuring. Missing PT is the only way to identify them. And muons are leaving the small fraction in electromagnetic and hadronic colorimeter. So it's like minimum interacting particles. So now let's talk a little bit about how we do the identification of the hadrons and why this is important. Jump. Do I have to point to some? So this is the, okay, yeah. Oh, no, it's back. Where's forward? Oh, this is okay. I mentioned to you that we have like about 200 particles in the particle data group, and we need to, the way how we identify the short-lived particles is by actually looking at the decay products. And this is one of the examples which I gave you during, to calculate the number of events which we are going to. So this is boson-gluon fusion. So you create the CC bar pairs, and we identifying those CC bar pairs going to the different directions, and they sort of produce the open charm. In this case, D-star mesons. And the way how we identify them, we just look at the vertex and the PID of the detector, right, or of the particle. So if we do not have any vertex detector, or we do not know what type of the hadrons we are identifying or we are measuring, this will be the invariant mass spectra which you can get. Like, it's simply because of the combinatorial background, you will not be able to see any dimeson in your experiment. But of course, if you apply, identification that it was a pion, this was a kaon, what is a displaced vertex, you will be able to, jump from this plot to this plot. Yeah. So this is sort of the motivation why we need the particle identification. And what is interesting that at HERA 1, so when we just started this experiment, we didn't have the PID and we didn't have the vertex detector. So what we saw is this continuous background. And only after the upgrade, when we installed the vertex detector, we were able to, so we didn't have the PID at that time, but we were able to extract the open charm signal. And another example, so here I just tried to see, so this is the no PID and no vertex. And if you just, include some of the PID, like 80%, you start to see the bump on the continuous spectrum. And if you require a vertex, 100 micron resolution vertex, but again, no PID, so you will see some bump here. But with a good PID and with good vertex, so this is what we are expecting to see at the EIC, you immediately will see, oh, this is the D0 peak. Oh my God. I need to work on a PDF, so something got wrong. So, I'm not going to talk about DDX measurements. So this is mainly done in tracking detectors, but it will require special electronics to measure the amplitude of the clusters. And we are not doing this at EIC. So that's why I'm not going to talk about this. I'm not going to talk about transition radiation detector, which can provide a good separation of the electron and the hadrons. I have a backup slide, so if you want, we can go back to this, because this is a proposal for the second detector for the future upgrade. But what I am going to focus is about on a time of flight and the Cherenkov detectors. Oh no, I include this little bit on the DDX. So this is actually the way how we identify for the low momenta. You can see if you measure the energy deposition, you can see that separation between the different particles are very clear if you plot this DDX as a function of the particle momenta. But there is a limitation, so we cannot really identify it with for the particles with momenta that higher than 1 GeV. There is some limitation. So let's talk about the time of flight. This is just the principle of operation. You have two detectors, start and stop detectors. You have two particles with a different mass. When they fly, they produce a signal in the start detectors, and then you compare with time of arrival on the second detector. Of course, if the mass of the particle is larger, it will take more time to reach the stop detector. And using this principle, you can identify this mass difference. This works very well, good for the fixed target facility. You have place for the start and stop detectors, so everything is fine. But in a collider, your particles are producing the IP, and there is a beam pipe, so there is no place to place additional detectors there. How do you identify the start of the time? Yeah, the starting point. And the scientists found a way. Of course, you can use the RF clock of the accelerator when the bunches are arriving to the IP. You can use this time, but this gives you some uncertainties in a T0, which is unacceptable for our case. What people found, and this is very common also in LHC experiments, so they are calculating the vertex of the particles, where the particles is produced, because you can do this very well with high granularity tracking detectors, and they calculate the particle trajectory, this L. And of course, if you know very well the time of arrival and you know the momenta, so you will see what will be the the time difference. And yeah, but of course you need to make sure that you have at least 3 sigma separation, because you need to identify the particles, right? For the time of flight, we are going to use the ACL guard detectors. They provide very, very precise timing. It's one of the, I haven't seen any with better numbers on a timing resolution so far. So it's 30 picosecond timing resolution. And but the pixel pitch is 500 microns. So the disadvantages of this, as I mentioned, that there will be electronics bombarded, so it provides material on the top. So we will place it like at the at the end of the tracking detector. So it will be outermost detectors compared to the tracking, but they will provide also tracking point, so which is really good for the tracking capabilities. Few words about the Cherenkov detectors. On this, this is a PFS simulation. You will see how the momenta of the particles for the pions and the kaons are distributed as a function of the observed rapidity. You see immediately that due to the kinematics, everything is boosted towards the hadron and cup. And this is sort of the provide the requirements for what kind of Cherenkov detectors we are really using. And what will be the coverage. So I'm not going to really spend the time on explaining you what the Cherenkov detectors, but you know that when the charged particles is traveling in a certain medium, they started to produce the Cherenkov lights, and you are detecting this cone and how it looks. And actually, what is interesting that the number of the photons which you are detecting are really small. So it's maybe an order of like 4, which you can really measure. So this is really challenging. So what in the EIC, we are going to use the proximity focusing reach. They will have aerogel medium, which will sort of generate this light. And then there will be some mirrors which will reflect those cones to the sensor areas which are located on the back of this vessel. And let's me go this, and in real life, so when you read the detector, so this is what you see instead of cone, because of the mirrors. So you will see like Pokemon shape structure. So if it will be somewhere, in the middle, so you probably will detect the full circle. And then you would have to, measure the radius of this cone, and this will give you, and also know very precise what the momenta the particles, and is that you can predict if it was a pion or a kaon electron. So this is the sensors. Also very good resolution. Could be also used for the TOF, so it will be used for the TOF in this area. And yeah, so we are right now testing that. We got a couple of units for testing. So it will be interesting to see their performance. So this is how actually we will do the separation. So if you plot the Cherenkov angle, so this opening of this cone, as a function of the momentum, for the different particles, you will see those curves. And this is how you sort of see whether you can separate and what will be the separation power. So I think this is the electron, this is pion, kaon, and the proton. This is how you identify the particles. But I think we can reach the, so at the 7 GeV of the momenta, you barely can separate pions and the kaons. You see they're like overlapping. That means this is will be our like range, momentum range, which we can provide the good identification. For the forward end cup, again, looking at this profile of the particle momenta, you see the particles will have quite high momentum. So maybe not 100 GeV, but 50 GeV for sure. And for that, we are going to use dual radiator reach. And one having it will have 2 radiators. Having one aerogel will not be enough. So we need the gas radiator for that. And with this combo, we sort of can provide the coverage for the low momentum particles and for the high momentum particles. The group already have the very good experience with this on the multiple reach detectors and dual radiator detectors were built, so we are confident that it will be happening. What is bad about this? So as you can see, the magnetic, it will be sitting in a solenoid. Magnetic field is not really uniform, as you can see here, and this will be the place where the sensor detector. So we cannot use the photomultiplier. So there will be IPMs, but IPMs create a lot of noise. So that means it will be hard. And I remember I told you that there is only like few photons which one can produce and detect. So they will be quite challenging for in terms of the identification. Yeah, and this is the readout, as you can see. The readout, the IPMs, so they will be over here, the mirrors, and our aerogel is in front, and the gas volume. So this is sort of the setup, and that covers the forward end cup area. As you can see, there is 2 curves showing how we do separation of the pions and the kaons and the electrons and pions. One refers to the aerogel and another one for the gas radiator. So this is sort of what we are using for the particle identification there. In the barrel, we need something because as you can see, there is simply no space due to the size of the solenoid. We need something readily compact. And the jerk, which is detection of the internally reflected chain of light. So when the particle is traveling through those bars, they provide a photon, or they produce the photons, and they are sort of starting to bounce in these bars, and then they reach the surface of the detector. And again, so this will be not you will not detect the full circle, full cone, but like a fraction of it. Those detectors, because we have only 5 centimeter space for them, so they have a limitation on how we on the range of the pi k separation. And we are going to reuse ballpark bars. So right now they are at JLab, and we are trying to refurbish them. So this is sort of the image, what you will see, like part of the ring, and this is just for simulation. You can see these bars, particle heated, and there is some lights transported through the bars. So will be very challenging. So again, we are looking towards the help of the machine learning algorithms to identify those semi-rings. So will be interesting project. And as you can see, this is what is the limit in terms of the electron pi and pi k and k pi separation. 3 sigma up to 6 GeV. Now let's, so we are done with the central detector. Now let's go to the far forward and far backward instrumentation. And this is really crucial for the EIC program, and I will tell you in a few minutes why. But here you can see the central detector in a hole, the beam elements in the gray over here, and yellow highlighted here and here our far forward, far backward detectors. And I will go one by one. So in total, we have 7 subdetectors or 12 subsystems. It's similar to the central detectors, but I am not going to really dive into the whole program, all details of this, but I will talk about challenges. And as you can see from this plot, because we are sitting in a tunnel, and there's a lot of accelerator magnets and beam elements, it really requires close collaboration with accelerator team, to make sure that the accelerator can deliver the beam, and from one hand, and that we as a scientist can measure what we. So let's start with the far forward physics. And here you can see the snapshot of the physics events which require forward tagging. Starting from the DVCS events, when you have to detect the proton or the deuterons, exclusive J-psi production, and name what, right? You will have a lecture next week with by Alex Jange. I think he will go over all the details of this. I just wanted to talk about the instrumentation, but this is sort of the motivation for the case of the detectors. We have in the far forward area, we have 4 subsystems. We have B0 detectors, which is sitting inside the dipole. We have Raman pods, which are sitting very close to the core of the beam. And we have the zero duty calorimeter. Off momentum detectors are pretty much similar to the Raman pods, and the way we are designing this, we would like to provide the smooth coverage between a central detector and this B0 detector, intermediate stage, and the far forward instrumentation, so that there is no gaps, and we really measure all detectors. And as you can see, we have to really measure the protons in quite a wide range of the PT, and there will be some particles with a different rigidity, and also the neutral particles, right? So, let's start with the Raman pods. So this is the example of Raman pods. So as you can see, the detectors over here, we are going as close as possible to the core of the beam. So the core of beam coming here. So those detectors have to be movable. So we have to be able to extract them or insert. They will be in a vacuum system. And accelerator people are really important because they provide some bad effects for the accelerator. So we are really working together to solve this problem. Off momentum detectors, as I mentioned, that there is some case where you have the particles with the different magnetic rigidities. So that means they are like bending more strongly in sets of the dipoles which are in front. So we have to provide the instrumentation. So they will be similar to the Raman pods, but they will not really be as close as, you know, as close to the core of the beam, but they will be sitting on our side. So this is how the Roman pods looks like. We are using the ACL GUT technology, the same as for the time-of-flight detectors. And this you can see the layout. So the detectors will be placed like around the beam punch, and they will be movable up and down to provide the proper spectrum. So this is the complicating, you know, mechanism for the insertion of those chambers, and we are still working on the shieldings and minimize the material for those particles, for those detectors. So I probably will skip this one because we do not have. What is really important here is to know that when we measure the forward particles, there is also some beam effects, like the angular divergence of the beam, or because accelerators are using the crab rotations to make sure that the punches are colliding sort of the head to head, and to compensate this crossing angle sort of. And we need to take into account all of those events and see what will be like the impact on the physics. This is nice sort of video showing how the bunches are colliding. And you can see the accelerated team is rotating bunches, and this is what gives the additional kick for the particles, which we sort of have to take into account when we do the extraction of the physics. So, and like linking those measurements to the physics. So this is an example of the like what we're going to measure with Roman pods and B0 detectors. As you can see, the Roman pods provides the low T or low PT measurements for the protons, and B0 detectors, they're covering the large PT area. So we need both of those detectors. Of course, there will be a gap, but because we are operating with a different energy of the accelerator, we can shift this gap one side to the other. So Alex will talk about different modes of operation. So I'm not going to spend the time here. So the B0 detector I mentioned already. So they're really important because they are sort of providing the gap between covering the gap between the central detector and the Roman pods. And they're especially important for the low energy operation. So if you just look at the angular distribution of the protons, you will see that for like low energy operations, so we need to cover the down to the 20 millirad the angle coverage for the protons. So this is what exactly those detectors will be providing. They will be sitting in the dipole. Right now, it's one of the most challenging in terms of the integration detector space. So you can see that the dipole has two beam pipes, electron and hadron beam pipes. So they are going on the angle because we have a crossing angle. They will be like Pokemon shape for the detectors. And as you can see, we do not have like literally we have 10 centimeter space in front for the installation of those detectors. And this is how they will look like. So this is a giant simulation or CAD simulation, I don't know. So tracking detectors will be placed and the colorimeters behind. So we hope that with 4 layers, we can achieve very good resolution for the particles. Again, Alex will talk about this, but I wanted to show you like how complicated the installation. So there will be like railing system. There is a vacuum valve which is sort of keeps the beam pipe under the vacuum. So those detectors will split it in a half, and some special like railings will be installed to slide the detectors in and out. So this is really one of the challenging subsystems. Zero degree calorimeter, so we need to detect the neutrons and the photons, so that we'll have two parts, electromagnetic and hadronic. The transverse size is 60 by 60 centimeters and about 2 meters in the length. And this comes from the requirements that we have to detect like 6 millirad of the cone of the neutrons, but due to the construction of the accelerator, we will not be able to capture a full spectra, so there is some limitation on that. But they will provide very good measurements for both for the electromagnetic and hadronic shelters. For the EMCAL, we are going to use the lead tungsten, and for the same as for the backward electron cup, and for the hadron, we are going to use the same concept as for the insert of the hadronic calorimeter, which I just described. I mentioned about the challenge with integration with accelerator facility. You can see this is the electron line, a lot of magnets and beam elements. This is the hadron beam pipe, and again, a lot of grab rotation modules and other subsystems. We have only like, less than 2 centimeter clearance. So we are sitting really, really close to the beam pipe, and this one of the neutrons indicated here. Yeah, and the radiation dose, of course, it's really important. So we need to understand, and we have a running simulation to make sure that those detectors can survive. I want to show you this slide because this is one of the interesting topics. It's still one of the most challenging, I think, to measure the EIC, how to understand the mass, and especially mass and structure of the pions and the kaons. So one of the process is indicated here on this Feynman diagram, where you sort of have in the final state, you're tagging not only the protons and the neutrons, but the lambdas, yeah? And lambdas are really, because of the high energy, or because they are sort of, will have the same energy as the initial proton, and 100 GeV lambdas, even so that they will decay, they will not decay immediately, yeah? So they will fly, and they will fly quite some distance. So they can fly even, like tens of meters before they decay. And you have to provide the measurements for the final products. And this is one of the challenging aspects. And the idea is that we place also the detectors here to identify the decay products. But some of them we can detect in the B0 detectors, but for some we need to sort of place detectors after the final focusing quads and other beam elements. So there will be some inefficiency in terms of the detecting capabilities, but we still hope that we can get some good results. So now let's talk, we have 5 minutes, yes. For backward instrumentation, so I talk about forward, so now let's show what is in the backward area. Here we have low Q-square taggers, and this is really, important aspects of the EIC program to provide the measurements of the photo production, so Q-square below 1 GeV squared. And we have 2 tagger stations here and there. And also this area will provide the space for the luminosity system. You can see over here. So for the low Q-square taggers, I probably do not have a time to go into the details, but you can see that due to the beam effects, at least in our current simulation, what we see, we can really, reconstruct the Q square down to the 10 to the minus 4. But beyond that, the beam effects will sort of, destroy our measurements. But even so that we will be able to tag them, but we will not be able to distinguish, in terms of the binning. And the rate is very high. So we need to have the detectors which can survive at this high rate. And we decided to use the time peaks technology. So time peaks is actually not the detector, it's a readout chip. It will be sitting, on the top of the silicon detectors. They have very high rate capability, up to 20 kilohertz they can cover, and good timing. So we can distinguish, bunch by bunch structure if needed. So probably not needed, but, and 55 micron pixels. And yeah.